Hello everyone, my name is Javier Nuñez and I'm a researcher at TNO, the Netherlands Organization for Applied Scientific Research. Let's now share my presentation. Today, I will be presenting this study entitled Chemical Identifier for Particulate Matter Monitoring in Construction Sites. And I'm honored to do it for the IEEE Sensors 2021 conference, also on behalf of the co-authors and colleagues Robin Koldeweij, Joe Trimboli, and Arjen Boersma. I'll begin with an introductory section, followed by the materials and methods we have used and our theoretical calculations. Next, I will elaborate on the results obtained, and finally, I will wrap up with the most important conclusions. During the introduction, I will talk about the context of the study and the working principle of the technology. A lot of research has been conducted to determine factors that can influence the predisposition towards health problems of an individual. The term genome gathers all the genetic factors that can increase the likeliness of suffering from a disease, whereas the term exposome refers to the totality of environmental exposures accumulating throughout the lifetime of an individual with a negative health impact. Since occupational exposure has an important effect on the individual's health, a proper characterization becomes essential to reduce its negative impact. In this study, particulate matter refers to the airborne heterogeneous material that is suspended in the air and that is responsible for negative health and environmental effects. For the characterization of particulate matter, there are various sensing technologies available out there. There are small, low-cost PM sensors that can classify particles according to size in these three categories, PM1, PM2.5, and PM10. However, for chemical identification, the common practice is to collect the aerosol in a filter and analyze it in a laboratory, which fails at providing information in real time. Other equipment, such as the aerosol mass spectrometer, are bulky and expensive. In this study, I'll present the PMCID, which stands for Particulate Matter Chemical Identifier. It consists of a mini FTIR-based PM sensor, which is capable of inline chemical identification, is portable, at much lower cost than other technologies that monitor chemical composition of PM in real time. The PMCID has the following components: an optical infrastructure that includes a mini FTIR spectrometer, a mini cyclone, a hollow waveguide, an automation system for autonomous acquisition, a data processing unit with a self-developed smart algorithm that interprets the data, and finally, a communication system that enables the reading and monitoring of mobile devices. The working principle can be summarized as follows. The cyclone samples the environment air and concentrates the PM. These particles then flow from the bottom of the cyclone to the hollow waveguide, where they interact with the infrared light of the spectrometer. Then the particles leave the waveguide at the other end and get trapped in a HEPA filter. The full system is automated to facilitate the cleaning of residual particles by flushing the hollow waveguide with higher flow rates. Now we move forward to the theoretical calculations used to design the mini cyclones and our data processing algorithm. We have based the design of the cyclone on the studies performed by Kenny et al. That state that for a fixed geometry ratio, the cutoff point depends on the body diameter and the flow rate. Additionally, we have done some research into the influence of individual dimensions in the overall efficiency by simulating its behavior with the modeling software console. This way, we could both validate Kenny's expression and optimize our own cyclone design. These are the final dimensions used for the cyclone of the PMCID. Regarding the data processing algorithm, we had to account for two important effects that particles have on the final FTIR data. namely the light scattering and the light absorption. Each of these behaves in a different way depending on the particle size, refractive index, concentration, and chemical groups. The PMCID combines two different processes to obtain the final concentration of individual components. On one hand, there is an optical particle counter present that provides extra information about the total PM concentration in the sample. On the other hand, the FTIR-based CID unit provides information on the chemical composition. Then, the algorithm combines both data streams to calculate the individual concentrations and send them to the cloud. We will now focus on the results of this study. First, we simulated different cyclone geometries to optimize the mini-cyclone for our application. In this figure, we can see the simulation results for Kenny's geometry in orange and for our modified geometry in gray. The simulation of Kenny's geometry validates the equation proposed in their studies, plotted here as a black line. Both the theoretical equation and the software modeling were validated experimentally by exposing physical cyclones to aerosols and monitoring the particle size distribution with an optical particle counter. In this figure, the experimental points in blue correspond to the cyclone modeled in simulation B, providing extra confidence in the numerical modeling. These are the FTIR responses to individual components. The CID was exposed to aerosols of pure compounds that are typically present in the construction industry, namely amorphous silica, crystalline silica, calcium carbonate, and calcium sulfate. These spectra were used to calibrate our data processing algorithm. As we have seen before, the raw FTIR features depend on two factors: the infrared absorption of the material itself and the light scattering. The particle size is comparable to the wavelength of the infrared light, and therefore Mie scattering plays an important role in the absorbance spectra of the samples. Unfortunately, Mie scattering is a very complex phenomenon. In this figure, an example of Mie scattering of amorphous silica is shown for different particle sizes, as calculated with the open source application Mie plot. Our algorithm is capable of compensating for the Mie scattering effects and includes the IR absorption features obtained from the previous calibration process. Moving forward, this picture shows the data fitting for a typical sample obtained with the PMCID. In blue, we can see the raw FTIR spectrum, and in orange, the fit performed by our algorithm. Several spectral features have been identified to determine the composition of an unknown sample. P1 is related to Mie scattering and gives information about particle size and concentration. P2 and P3 are associated to free water and water of hydration, respectively. P4, although not present in this sample, relates to carbonate content. P5 and P6 to crystalline silica and total silica content. P7 to phosphate and silicate content, and finally CF refers to the Christiansen feature. The latter represents a minimum of back scattering when the refractive index of the material, which is wavelength dependent, approaches that of the surrounding medium at a certain wavelength. This feature provides additional information about the silica content of the sample. Finally, the calibrated PMCID was tested with specific target aerosols, and the experimental results were compared with the literature values associated with those materials, as shown in this table for sandstone and aerated concrete. The information obtained with the PMCID was comparable to that of the literature, which validated the sensor for its use in construction sites. Wrapping up, we have drawn the following conclusions out of this study. A fully automated chemical identifier for particulate matter has successfully been developed based on the occupational exposure study case. The PMCID is based on FTIR and features a smart algorithm capable of reading and interpreting the complex features found in the spectral raw data and translating them into composition percentages of individual compounds. The unit is portable and permits the near real-time monitoring of aerosols. Finally, the system incorporates a cloud infrastructure for remote monitoring on mobile devices. Thank you very much for your attention. It has been a pleasure to present our research work in the IEEE Sensors 2021 conference. I'm glad to answer any question you might have about our study. Thank you and goodbye.